Good morning. It's good to see many of you who I haven't seen for a few years. A few years ago, I think when we did the tutorial, I showed you this picture of 1984 Wabot who is supposed to be able to read music, play the camera, and play the organ. And I said, you can see, actually, the robot's still there in Tsukuba, Japan. But since then, I found a video of this robot playing at the expo. See if this works.
楽譜を読み取って演奏するロボット。
At the expo in 1985. Supposedly reading music real time. Questionable, but I thought entertaining a little bit for that. All right. So plan for today. I'll talk about the Rodan workflow management system, its layout analysis, choose pixel for annotation, and a couple of cool deep learning methods for that. I'll talk about what's called the new mapping tool, interactive classifier, OCR and text aligner, Neon for correction, and finally, Cantus Ultimus for viewing and searching. So we're concentrated in early music notation, basically called Neum notation. The problem that we have is because this is Common Western music notation, definitely before even menstrual. So the notation system were not standardized. So we have lots of different types of looking things, and it'd be really difficult to train this with deep learning because then you need lots of annotation, which we don't have, and it'll be. I mean, there aren't that many of these things, right? There's maybe tens of manuscript for each of these notation. So it's not, if you're going to annotate them, you're done. You don't have to train anything. So, but we wanted to do this as efficiently as possible. So we have a system called Rodan, which was basically Andrew Hankinson's PhD. And this is basically what the workflow looks like. It's basically a graphic programming. It's like Max MSP, if you know that. So you can just plug things in. And this is basically the whole thing. Can't use the pointer, but here, you can put the images in here, and there's a layout which comes out with 3 different layers. And once it's done, you combine them together and you do some editing after putting in MEI. So this is basically the workflow you're seeing. So I'll go through this in a little more detail for that. So typically in early music, and this is from this beautiful Salzin manuscript, which is usually in Canada, but it's now in Namur, Belgium. It'll be displayed there till January. So we first converted to grayscale. We do some binarization. We remove the borders. We do the lyric removal. Then we do the staff removal. Then we finally can do some symbol classification, right? Then we put the staff back in so that you know what the pitches are, right? Then finally, we put everything back together so you can find things on the actual facsimile. Then something happened in 2016. No, it was huge. It was done by Jorge Calvo, and it's basically a pixel level classification. And I thought this was totally crazy because typically these manuscripts about 30 million pixels. And Jorge said, well, we're going to annotate every single one of those pixels. Then we can do real cool stuff. And then you're nuts. How are you going to annotate 30 million pixels per image, right? So what the whole point was to be able to figure out what's background, what's text, what's staff lines, and what are the musical symbols. So it's like a 4 class classification. And he used CNN and we called it Calvo's method. He doesn't like it, so don't you ever call it a Calvo's method. But yeah, no, it was amazing, and it works, but you still need but what was amazing is that all these steps that we had, the first 5 steps is now can be done in 1 step. And this is more than saving steps, but as many of you know, any errors that happens earlier in your workflow propagates, right? So you want to be very good at the beginning, and this actually did that for us. All right, so just let me go through the whole thing. This is SIMSSA workflow for new notation. You have your manuscript, you do this amazing layer analysis, you do the symbol classification once they're separated, and we have to do what's called a new mapping, which I'll explain in a bit. Then we do some pitch finding and do the lyric alignment, which has to align the neumes with the text. And we get some information, what's called a Cantus database, which basically has all the text already entered. Then we do some MEI output. Then we do the corrections, which is important, as David Weigel just told us. And then we show it in Cantus Ultimus interface based on IIIF distribution. And we also use metadata from Cantus for that. And the whole thing is we call Rodan. So back to this layout analysis, basically it finds 4 layers, the background, staff note, and text. Okay, so in order to annotate this 30 million pixels, we created a tool called pixel.js. Basically allows you to create these ground truth by selecting whether something on the page is one of the 4 classes. So this is what it sort of looks like. It's color coded. So the green will be staff line, blue will be music, and the red will be the text. So we did this, and to annotate 1 page of a manuscript containing over 30 million pixels took 24 hours straight. So that's 3 days. And that's a lot of work. And we did that for a few pages, but we knew this wasn't going to scale. So we decided to do what's called a partial creation of ground truth. So we don't do the whole page. We just do parts of it and then train it, then have it classify, see how well it does. And where it failed, we annotate again. So it's sort of incremental training. So here's typical original image, and that's what the annotator had to do, right? You'll notice that it's the text that takes more time than anything else. Mostly staff lines are more or less straight. The square notations are square, so they're fairly easy to mark up, but the text was a real struggle. So we have solution for that. I'll talk about that. But here's the results of the classification. So the left-hand side is the original. So you can do this is not the annotation. This is the classification result after training. So, and then we have a staff, because these are done separate, right? And you put that on. It's looking very good. And then we put the text on top, which is also good. Then here's the result. Note that the background is white, so it knows what the background is, right? So this is very good. Okay, so, but we had this problem annotation, even with this partial annotation, it took a little time. So we went from Calvo's method to Paco's method. It's made by Paco. And how he does this will be presented, I think it's the last paper today. And he'll also present at Izmir next week. Yes. So the big thing was we decided to do the background separation before we do the layout. Because if you think about it, the text is almost always against the background, right? So if you can remove the background, just the text just surfaces by itself. You don't really have to separate it. So you can just put a box around it, and anything inside the box will be text. The background is not really there. So that reduces the amount of time required to annotate text. And we keep doing the partial annotation, and we do the strategic interactive annotation and training. So you learn what it's learning. So you get better at teaching, and that's how we do things. So here's the final result, and that's what it looks like. And the strategic interactive teaching reduced the creation of training data from 24 hours to 6 hours. That's huge when you have to pay people to get it. Even for, people, even if you ask people for crowdsourcing, it'd be much easier on them. Okay, so let's briefly about MEI for NUMS, which is a little bit different. So this was started in 2010 by Stefan Morant, and we formed a special interest group in 2013. And whoop, I went too fast. And there was a new schema that was introduced, and it was introduced as MEI4 in 2018. So we're still trying to modify from that change. So talking about this new mapping tool. So even if you classified all these different symbols, we have to eventually encode an MEI. And each of these different NUMs will have different encoding schema. So these are things like, there's a curve, and there's a tilt to northeast, right? So we have these sort of shape descriptions because there's just too many variation on the form of these NUMs. So we decided to do that. So that was the big change. And there's more. It gets quite crazy. So we have to provide, and these are provided by musicologists, how these symbols are encoded in MEI. So we make that task a little easier where they can upload their spreadsheet or Word file, Word table up, and they can edit for that. And so given that, and we have this interactive classifier, which be able to classify quite quickly using k-nearest neighbor classifier. And after that, we have the OCR text aligner. It's done by Tim to reduce, who's almost graduating with his PhD. And so the trick is to figure out what the text says, right, and where they are exactly. We know what the text says from the Canvas database, but there are crazy things like rubric, which is the direction. They're usually in red, and they're abbreviations, which is not exactly what's on the page and what it's supposed to. So those things has to be sorted out. Every singer of this music knows how to unabbreviate these things. So OCR uses calamari, which is LSTM, and there's sequence alignment to figure out how to match these words. And after that, we separate them, and you can match with the which NUMs it belongs to. So NUM notation is really, it's an annotated text. Text is the main thing. That's how it started, right? So you have the text sort of to make you remember how you sing it. They annotated the text. So getting the text in NUM is very important. All right, let's go talk about the editor. So this is specific for NUMs. Maybe if we had MEI friends, we wouldn't have gone this route, but it's basically the same thing. Use Verovio for rendering. And we also use IIIF as the input to the image. This is people have been working this for several years now. It's getting quite nice, easy to use, specific for NUMs. All right, and once we're done with all that, we can put everything on what's called the Canvas Optimus interface, and where you can go page by page. And these are what's called the volcano text. Some of these are entered manually, but if we do the OMR, we can actually search by NUMs, right? and know exactly where they are because of the zones in the MEI files. And Neon can actually, theoretically, I mean, you can basically, when it works, you can do multiple pages, not just one page at a time. So we have a lot more manuscript OMR. We have collected. So these are all have IIIF and have text information Canvas database. So we've done 2 out of 18. We're working on the 3rd one. It should get faster as we go. We're debugging the whole system as we go. So that's why it's taking quite a while. So we talk about the Rodan workflow management system, layout, new interactive classifier, OCR text aligner, JS correction, and Canvas Ultimus for viewing and editing. And many people worked on this project. It's been going for maybe 10 years now. Yeah, we were online for a couple of years. We're finally back in our lab this summer. These are people, yeah, you might recognize Andrew Hankinson. Okay, thank you very much.
We'll try to keep the Q&A short because we'll have a final session at the end for the papers. So I think I'm asking 2 questions. Do we have any questions?
Yes. Thank you for your presentation here. I wanted to ask you about the alignment between nodes and lyrics. Like, how does the process work for performing alignment and to assign a certain lyric or syllable to a specific thing?
So it's basically proximity and the number it has to match. So the alignment algorithm figure out how many syllables against how many neumes or above, and they'll try to figure that. And that's the alignment. And other than that, it's proximity.
How do you separate the neumes by between the groups, or
well, neumes, because they're very close together, right? Yeah, neumes are either connected together or separate. So we know number of neumes, and we have to figure out number of syllables.